So the final part of our overview lessons will evaluate all the Java programming paradigms that we've talked about in this class, and hopefully ones that you've brought with you from other courses where you learned about Java. And we're going to talk about things like object-oriented programming, including structured concurrency, and synchronous and asynchronous functional programming. We're going to basically come up with a nice little fourfold chart, it's kind of a quad chart, that'll allow us to be able to compare and contrast the different paradigms and see what the pros and cons are. And in particular, we're going to focus on the good things about reactive streams versus the alternatives, as well as the downsides, the drawbacks of reactive streams versus alternatives. So here's the overall perspective of Java programming paradigms. You'll notice we have two dimensions in this quadrant. We have the synchronous versus asynchronous properties. This is really do things block versus not block, the color. And then we have how many values are involved in a typical operation or operator. Is there one value, one return value, for example, or is there a stream of multiple values? So those are the two dimensions we're going to look at here. And then we're going to use that to classify the different paradigms. So let's start off with the most basic way of doing things. This goes back to the dawn of time in programming, object-oriented programming back in the 70s and 80s, where you have objects that have methods, and when you call those methods, the thread of control of the caller is borrowed to run the method. And there's typically a single value that's returned, which is either some kind of primitive, some kind of scalar, like an integer or a string, or it might be a collection of stuff, but there's one thing that's returned. And here's a very simple example where we're going to have a method called download content. We give it a URL, and it allocates a buffer, and then it opens a stream to the content at the URL. And while we haven't finished reading all the content, we keep reading till we reach the end of file, and we store each chunk of buffered data into some kind of output stream, which will then ultimately be returned back as the return value from this function. So just very classic way of doing things. What's interesting about this is that Java virtual threads and very modern Java structured concurrency are making synchronous programming cool again. So for years, synchronous programming wasn't very cool, so people came up with all kinds of other ways of doing things. But now these new features are making it cool again for people who never really wanted to learn the new paradigms. It's kind of like if you buy clothes, those clothes will sometimes go out of style, but if you wait long enough, they'll come back in style again. So it's like fashion or music. So that's sort of both the early beginning way of doing things and now the very modern Java way of doing things is through objects with single values that make synchronous invocations. The next turn of the crank, and by the way, this started in 1993 or 1995, depending on when you think Java started, and it's been around ever since. So gosh, that seems like a long time. It's basically 30 years worth of stuff. Another paradigm that emerged in the 2014 timeframe was the streams paradigm, where a stream, be it a parallel stream or a sequential stream, uses synchronous calls where you're blocking, but you can have multiple values. So here's a simple example where we're going to take a list of URLs. We're going to make this into a parallel stream. We're going to get rid of everything that we that's been cached before. We're going to ignore things that are cached. We're going to download everything that wasn't cached, and we're going to apply some image processing filters, and we're going to return the results as a list. So that's sort of a classic stream approach, and notice we get a set of multiple values in this case. In this case, we turn it back into a single return value, but we have a stream with multiple values, and the operations that are being applied here work on the multiple values in the stream. And you can either do this sequentially or in parallel. I like this paradigm quite a bit. It's pretty darn easy to understand. Once you understand how to read functional programming and compositional logic with streams, and it's trivial to parallelize it or not using parallel stream. The next turn of the crank, which also ironically came out in the 2014 timeframe, was completable futures. And completable futures are asynchronous because you start operations and they run in a background thread without blocking the caller, but they produce a single value. So here's an example where we're going to take a big fraction and we're going to start it running in the background to do something with it, reduce it, for example. And then we're going to take the results of that asynchronously and convert the improper fraction to a proper fraction, a mixed fraction, and then we're going to print the results out. And all of this is going to run in the background in a thread without blocking the caller. But there's a single value, which is, in this case, either the mixed string and or the results of printing things at the end of this little set of actions that are performed. These are called completion stage methods in the completable future parlance. So this is a nice approach. The problem is most people have a hard time getting their head around asynchronous programming, and completable futures is very efficient, but the patterns are a little bit inscrutable unless you really get to understand how asynchrony works. So as a consequence, the first generation of reactive programming was to take streams, like sequential streams, and combine them with completable futures, much like a Reese's peanut butter cup that combines tasty chocolate with tasty peanut butter, and now you have something even more tasty if you like peanut butter cups. And what we have here is something where we take, for example, a stream of URLs, and then we asynchronously check to see if they've been cached, download them asynchronously if they've not already been cached, apply filters asynchronously, collect the results into a single completable future, and when everything is done, we log the results. So this is a nice model that combines the flow managed, the sequencing managed by streams, in this case a sequential stream, with the asynchrony provided by completable futures. So we get kind of the best of all possible worlds. I like this model quite a bit. The problem is it, again, takes two somewhat esoteric topics and joins them together. And while it works, you really have to understand the patterns of this type of programming. So therefore, the brave new world of reactive streams came out, which basically made a more seamless integration of streaming for control with asynchrony to be able to run things in the background, and then bake that into the programming APIs that you work with. And this is a RxJava implementation. We could do a Project Reactor one. I should probably do a Project Reactor one too. It doesn't really matter. They're almost identical here, where you're going to take a list of URLs, turn it into an observable, which could also be a flux if we needed to, convert that observable to a parallel observable, run that parallel observable on a scheduler, and then you download and store each image, which will then run in the background in one of the threads from the scheduler thread pool. Then we collect the results back into a list, and we wait until we're done, and we return a list of images. So this is the RxJava way of being able to get this capability. Now, for my money, if all was said and done, I kind of like this approach the best. The parallel streams approach is really, really convenient. It's not super inefficient. It's efficient. Chances are the version that combines streams with completable futures will be a little bit faster. And depending on the time of day and what version of software you use, this version may be fastest. But I think it's a little bit more complicated to understand than that version from parallel streams. Be that as it may, those are the different paradigms that have emerged in Java over time, and you get to choose which one you like best after you complete the course and get a chance to play around with all these different ways of doing things. So let's talk about the pros and cons of the Java reactive streams platforms. So there's a number of benefits, good things. One is minimal resource utilization. This was actually the driving force that spurred folks to do reactive programming initially. And a lot of the reactive programming work was initially done by Netflix. And they were trying to manage lots of hardware using lots of event streams, which are people with their controllers selecting movies and streaming the contents and so on. And so they were really big into this. And they wanted to be able to get maximal utilization of their hardware, because every time they added new subscribers, they didn't want to have to go out and buy more and more servers. So the idea here is to support concurrency with a minimal number of threads using a range of thread pools. So here's, for example, the RxJava thread pools, as we talked about before, and Project Reactor has very similar ones. The goal here was to scale up performance with relatively few resources. And back in the day, people had done some performance tests, which you can read about here. And they compared and contrasted the approach to having lots of concurrent users using traditional web MVC-like approaches that were synchronous and had lots of threads running around, hundreds of threads, versus the approach that used reactive programming with things like Webflux. And what you can see here is the number of users go up, the latency stays low for the asynchronous or reactive approach. Whereas for the synchronous approach, as the number of users go up, the computational effort increases, and therefore the systems can't really keep up with that. So that was a lot of the initial motivation for using reactive streams. Another nice thing is that it hides the accidental and inherent complexities of concurrency. You don't have to know about creating threads. You rarely have to know how to lock or synchronize, as long as you're careful in how you partition your data and whatever sharing you may have between the different computations that can run asynchronously. So this alleviates a lot of those inherent complexities. Now, to be fair, Java parallel streams, Java completable futures do the same kind of thing. But this is just one of the other benefits you get from reactive streams versus, for example, the traditional object-oriented way of doing things. And as I said, these benefits are not unique to reactive streams. Other things can give you similar benefits. Another nice thing is the seamless integration of these different paradigms where you integrate concurrency and asynchronously out of the box with one set of APIs rather than having to learn two sets of APIs and then learn how to join them together. Again, not the end of the world to do that integration of, say, streams and completable futures, but it's easy for me to say because I've been teaching this stuff for a long time, so it seems very natural. One of the other nice things you get with reactive programming is you can make asynchronous processing look very similar to synchronous processing. So it looks like these things are running synchronously. You can kind of read it from top to bottom without having to stand on your head and play all kinds of tricks with asynchrony. However, asynchrony is what's happening in this programming abstraction, even though it looks like synchronous programming. But not everything works with reactive programming. There's some things that are not well suited for that. It's not appropriate for all situations. The most common knock against reactive programming is it's more complicated to learn. The learning curve is higher. And that's primarily because most people who program started out learning imperative object-oriented programming. That's what we start with here at Vanderbilt, for example. When you start by taking the CS 1101 class and the data structures class, you're learning classic object-oriented programming with all the pros and cons of that. I often like to joke that I'm a recovering object-oriented programmer. That was my background, my tradition, but over time I've learned that there's other paradigms that work more effectively. I still respect what I learned from OO about abstraction and being able to scale things up through inheritance and dynamic binding and so on, and having better structures and encapsulation. But modern paradigms are actually more effective in a lot of ways for doing computation. So what you can see here is shown by this graph, and this comes from this video, which is a talk by Thomas Newkowitz about reactive programming pros and cons. And the basic point he's making is that if you have a small project with people who don't really understand reactive programming, you're probably better off sticking with a traditional way of doing things. And it's not until you get large programs, large systems, complicated systems with developers who understand reactive programming that you really start to see a win from doing things with reactive programming. And again, your mileage may vary where you end up with on this curve. Debugging can also be hard using asynchronous operations, using concurrent operations, and that's due largely to the lack of meaningful stack traces. So when something goes wrong and you do a back trace to see how you got to where you are, you'll often find only some pieces of the code you have any inkling of, and everything else is running in some asynchronous context. Now, if you don't write bugs in the first place, no problem, right? You don't have to worry about debugging your code. But that's of course easier said than done as well. So the basic point here is if you want to get the benefits of reactive programming, you have to climb the learning curve in order to use it effectively. So otherwise, you'll get good performance at the expense of productivity. What you really want is to balance it out so they're both going to give you good results. There's a very interesting video you should probably watch by Brian Getz, who is someone I respect quite a bit. He's one of the chief architects of Java, has been heavily involved with lots of stuff over many years. He's written some books and articles on concurrent programming. And his perspective is, especially in the context of microservices, are that Project Loom is what we now know as Java Virtual Threads and structured concurrency, is going to kill reactive programming. Now, I don't entirely agree with everything what he's saying there, but I do think he has a very important point, which is, since the vast majority of people are familiar with synchronous programming using objects, and structured concurrency and virtual threads support synchronous programming using objects, it should come as no surprise as those features become rolled out into the Java ecosystem, that more people will be able to be using concurrency effectively without having to master the more, quote, esoteric paradigms like reactive programming. So it's certainly food for thought. This is particularly interesting in the context of Java structured concurrency, where what you basically do is you take some high-level request, and then you use structured concurrency to split it off, typically by using something like either the shutdown on success or shutdown on failure model, where you farm out a bunch of work to a bunch of other microservices running in different computers in your cluster, and then you get all the results back, and you join them together, and you return a result back to whoever called you. So that's typically called like a scatter-gather style processing, or sort of fork join or map reduce kinds of things. And I think it's certainly worth considering that structured concurrency gives you a win here. However, we're going to have fun and we're going to learn reactive programming with microservices because it gives you a totally different and novel way of looking at the world. So you can decide ultimately, after you've had a chance to play with these different styles, which one is best suited for you. So that's the end of our evaluation of Java programming paradigms.